voice is reaching to each one of you. We are again in the module 1, and uh, in the previous discussion we have started the slicing strategy, that is how do we need to slice our CAD model or the given geometry that we are supposed to use in our 3D printer or additive manufacturing machine, right? So in slicing strategies, we have discussed two types of slicing strategies. That one is top-down slicing approach, and second one is your bottom-up slicing approach. And in both these approaches, in top-down slicing approach, what we were seeing, that suppose this was our actual profile that was supposed to be created using our 3D printer or AM machine. What we are doing, we are discretizing. We are dividing the whole part in 2D structure, or you can say some 2D contour of uh, uh, 2D contour of your given CAD model. Okay, so for this, what we are actually doing, we are having certain layer height. Suppose you are having layer height Z. So for each layer, you will have layer height H, and these are equidistance your layer through which you are trying to slice your CAD model. Okay, so all these are your slicing layer, and suppose from, because we will be counting from bottom side, so let us count. This is slice layer number 1, then we have layer number 2, then we have layer number 3, 4, 5, 6, 7, 8. Okay, so these were the slicing layer which we were discussing in our previous class. And what we could see, that in the top down approach, that is when we are considering the top corner of our given layer, or the layer which is under consideration. Okay, so for example, let us consider this layer number 1. This is our layer number 1. Okay, so for in this case, uh, if we take a top down slicing approach, we have to consider this particular vertex. Then for second layer, which vertex we have considered, this vertex. Then for third layer, this one. Fourth layer, this one. Fifth, this one. Sixth, this one. Okay, so what we were seeing, as there is change in the slope, the there is oversize in the part as well as undersize in the part. Okay, so that we have seen in the previous class, that how this undersize or oversize is seen in our profile. Similarly, in the case of bottom up slicing approach, in bottom up slicing approach, again, what we are considering, we are considering the bottom vertex of our given layer. Okay, so for layer number 1, we have taken this. Then for layer number 2, we are taking again bottom side, this one. So if you compare this with our previous, that is top down slicing approach, the it is actually, you can say, when you are comparing with our top down slicing approach, what you are seeing, in the case of your top down approach, the negative slope result in undersize. Here you can see, when the slope is positive, you can see oversize is there, and if the slope is negative, you can see there is undersize in your part which is being printed. Yes. Then it comes to the bottom up approach. So in bottom up approach, what we are seeing, in bottom up approach, when your slope is positive, this is here we can see, when our slope is positive in this particular region, so what is happening, it is resulting into the undersize. Okay, and when the slope is positive, like in this region, what is happening, it is resulting into the negative slope is resulting into the oversize. So we have to make you can say a balance in between these two methods, like where we have to choose the top down approach, or when we should use the bottom up approach, right? Depending upon our requirement. Okay, so like when there are two types of slicing approach by the combination of these. Maybe you may be desired uh, to have positive tolerances, like you may like to print oversize, but you don't want undersize component. Okay, so or undersize part in your part profile. So what you will do, you will simply give you will apply uh, the bottom up method when slope is negative, and bottom down method when the slope is positive. Okay, so this is the first case, that is corresponding to your positive tolerance slice. Then second case is related to your negative tolerance slicing. That is, you have to always choose the approach which is corresponding to the undersize, not corresponding to oversize. Okay, so the profile should not go beyond the desired profile of our final product. Okay, so depending upon the requirement of our printing, or the part which is needs to be fabricated, we have to choose we have to pick a balance between these two approaches. Okay, so here you can see through this final one diagram, that what are the advantages of these approaches and how these approaches are applied. Just a second. Yes, so here you can see the first figure A corresponding to your ordinary slicing approach. Here what you are seeing, you are having the 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 approach is top down approach. It means you are always considering your your top vertex. So here this is top down, again this here it is your top down, again top down. Okay, so the whole part has been divided, all the whole part is being sliced by using your top down approach. Okay, then it is it is the normal procedure, or you can say the normal practice which is done in AM machine, but you can slightly modify it, like in the second case what we have done, because in starting what we are seeing, the profile is the slope is positive, so we are seeing the oversize in the component. Okay, and similarly when the slope is going to be negative, it is resulting into the undersize. Okay, so in order to compensate, suppose we require that the product may go oversized, but it should not go underside. So what we have to do in this profile, what changes we have to do, as soon as we are going or the slope is going to be negative, we have to choose the bottom up approach. Okay, so as soon as the slope is becoming negative, we will use the bottom up approach. Okay, so here you can see from the layer 5th onward, we have used in this particular case layer 5th onward, 1 2 3 4 5. Okay, so up to 5 the slope is positive, we can go with the top down approach, but beyond 5 what we are seeing, because we are supposed to create the object which is having oversize but not the undersize, and but in our ordinary situation, because it was having undersize, so what we have done, we have chosen the bottom down approach. Okay, so sorry, bottom up approach. So here what we have done, beyond layer 5 we are using the bottom up approach, so we are considering bottom layer vertex, and accordingly we are getting oversized component instead of any undersize in the whole profile of our component, which is supposed to be printed using your 3D printer. Okay, yes. Then it comes to the another case when we have a profile that, or we have to use the component at some locations where you cannot have oversize. Okay, where your the case is that oversize is not permitted. Okay, maybe the part needs to be fit at a location where oversize may not fit properly. Okay, so in this case what we have to choose, we have to again rethink about this, and for printing or the slicing this particular component, what we have to do, we have to uh, uh, go with negative tolerance. Okay, negative tolerance, that we have to always choose the oversize sorry undersize of your given layer. Okay, so in this case, because the slope is positive in this particular region, what we have to choose, we have to choose bottom up approach. Then beyond layer 5, beyond layer 5, uh, because this slope is negative in this particular region, so what will happen, if you continue with our bottom up approach, it may result into oversize. Okay, so we are changing the approach, and we are using the top down approach beyond this particular layer, that is the layer number 5. So here this is what has been shown here. So this is corresponding to oversize, this is corresponding to undersize, this is about your ordinary situation. Okay, so this these things we have to make a balance, we have to take care of the profile of the component which is supposed to be printed. Okay, and this is at the level of layer. Okay, then it comes to the facets, because in these layers we will have definitely, because we were saying that we can represent these 3D CAD surfaces by the triangular surfaces of a triangular surfaces, and each triangular surface is having three vertices, like in this tetrahedron. How many triangular surfaces are there? There are four triangular surfaces. Okay, this is a tetrahedron. So maybe these if you enlarge these layer, what you will see, uh, uh, you will find that your slicing layer or your cutting plane may uh, lie at any point. Maybe it is above it, maybe it is after this one vertex, maybe it is after two vertex, maybe it is after three vertexes. Okay, so for any triangular surfaces, it may be below all vertexes, above all vertexes. Okay, in between, it may cut one vertex in one side and other two vertices on another side. So this we are going to discuss, that how this facets are considered in which particular segment. Okay, whether it will be considered in upper layer or lower layer. So yes, so the case may be like, first case, your cutting plane or your slicing plane may pass exactly through this your vertex. Then it may then uh, another case is when your one vertex may lie in one side, and first case is the cutting plane is passing through, or your slicing plane is passing through your one of the vertex. Okay, and second case is your slicing plane is not passing through any of the vertex, but it is passing in it is slicing the two surfaces which are connected by these remaining two surfaces, remaining two vertices. Okay, so like here, what is the position of your slicing plane? It is here. Okay, then third case may be your slicing plane may pass through two vertices, like vertex 2 and vertex 3. Okay, and it is not passing through the vertex 1. It is obvious. So these may be the cases when we are slicing or slicing our model during your slicing process. Okay, so during this slicing, what we have you know in any slicing plane or your or you can say your cutting plane, you can have a you can set a tolerance limit like some value like zero point 0.2 micrometer or something, zero point 0.2 micrometer depending upon your size of your triangular facets. Okay, so suppose uh, let us not discuss about units. Let us say it is suppose 10 unit. Okay, maybe this is in micrometer. Okay, so suppose it is 10 and you are having a your slicing plane which is passing through this z height which is written as your layer thickness, and you have you can say you are having a tolerance of 2% or 5% plus minus. Okay, 5% plus minus. Let me erase it for clarity. Okay, so it means your slicing plane may pass 5%. If any vertex, if your horizontal plane is passing or any vertex which is lying in between this particular tolerance region, the plane will be considered that it is passing through this particular vertex. Okay, so this tolerance limit we are considering in order to reduce or reduce the memory uses or save our time in slicing these CAD models. Okay, so these are the few cases that we will be discussing in this today's discussion. Like the first case is it is very simple. There are four cases basically when we are slicing these triangular facets through this horizontal plane. The first case is because I guess it is clear to all of you that we instead of a slicing plane we are considering a tolerance zone. Okay, this is our tolerance zone, or you can say bound tolerance. Okay, so if any point or any vertex is falling in between this zone, we will say our slicing plane is passing through this vertex. Is it clear? I hope. Yeah. So the first case is that is the case of group number 1. In this your this is a normal case where your intersection is away from the three vertices. Okay, so suppose it is your slicing plane, and this is your tolerance plane. Okay, and you can see here your this slicing plane or the tolerance within the your tolerance zone, none of your vertex is falling. Okay, so this is the simplest case, and then we have second case. Yes, just a second. Yes, yes. Uh, I, you can reconnect. Okay, no problem, because it is visible to everybody. So it might be. Okay, okay. You can choose my screen and click on the pin. There is pin profile. No problem. I'm saying I'm trying. Okay, just a second. Yeah, I hope now it is visible. Yeah, very good. So in the first case, I guess it is the simplest case in which your this your none of your vertex is falling in between your in between your tolerance zone. Okay, so since none of your vertex is falling in between this, so what we will consider uh, this uh, this will be considered as a you can say it your upper portion intersection of these portion, we may consider that this may be taken into the upper portion and this may be taken as into the lower portion. Okay, then there is second case. uh, in second case in this case, the second case is your one vertex may lie in your cutting plane or your slicing plane. So these are the cases where your cutting plane, one vertex may lie in your cutting plane. Suppose you are having a triangular facet like this, or like this, or like this. Okay, so in all these three cases, what is happening? Your one vertex is lying in between your in between your tolerance zone or your cutting plane. So in this case, what we are doing? Just a second. I hope network went. Students, I guess you can hear me because there was some network glitch. I have connected through my personal network, college network. Perhaps it's not working. Okay, so uh, this is the case where what we are seeing. Uh, our one vertex is at least one vertex is lying in the cutting plane, and this can be subdivided into three regions. If the remaining two vertexes lie is in the different region, the segment is valid. If they are in the same region, it is ignored. Okay, so here we can see in the first case, your one vertex is lying in between these your uh, uh, in between your cutting plane. Here also, in this particular triangular facets, your this vertex, single vertex, is lying in between your cutting plane, and here also the same, your vertex is lying in between in your cutting plane. Okay, then there is third case, that is the two vertexes lie in the cutting plane or your tolerance zone. Okay, so here suppose this is the case. So here how many vertexes are lying there? One vertex is there and two vertexes there. Okay, so uh, it means since there are two vertexes, uh, uh, this means it is the concurrent case that result in duplicated line segment, and one of them should be ignored. Okay, so because since two vertexes are lying there, you may consider it either in upper part or lower part, depending upon the choice of your user. Okay, then there is another case, group number 4, that all of your vertexes may lie in your single cutting plane. Okay, so yes, so these are the all four courses, and maybe I will stop here because today I was just wanted to discuss in short. Okay, so if there are any query we can take, otherwise on the Wednesday we will take one case study related to this slicing. Okay.